Hi friends, this is Rashekar, a GET faculty for electrical machines. Today in this video, we are going to discuss about Scott connection. Let's see here. Scott connection nothing but the conversion of two-phase into three-phase or three-phase into two-phase, vice versa. Conversion of two-phase to three-phase and three-phase to two-phase is called Scott connection. Here we required two transformers, two single-phase transformers. Here we require two single-phase transformers. Let's see here how they are, the two single-phase transformers. For example, this is the first transformer's primary, and this first transformer's primary cuts the second transformer's primary exactly 1:1 percentage, exactly 1:1 percentage, or 50:50%, 50:50% or 1:1%. For example, this is the first primary and this is the second primary. This first primary cuts the second primary in 50:50. That's why this transformer is called teaser transformer. Teaser transformer. And this transformer is called main transformer. This transformer is called main transformer. And its secondary is there. For example, this is my secondary of the teaser transformer, which is connected to the load. For example, this is VA and here the current is IA. And here the secondary of this transformer is, this is secondary of this transformer, which is connected to the load, which is equals to VB, and here the current is IB, and here the current is IB. See here. So here, these are the three phases. These are the three phases. And here we have only two phases. Here we have only two phases. For example, this is number of turns N, and this is number of turns of the teaser transformer. Number of turns of the teaser transformer. Anyone take, for example, this is primary rate and this is secondary N2. And here also this is secondary rate and this is primary N1. This N1 is here N by 2 and here also N by 2. These are divided into two parts, N1 by 2 and N1 by 2. And this is N2 number of turns. This is also N2 number of turns and this is N. For example, this is point A and this is point B and this is point C and this is point D. This is point D. For example, here the current is IA, here the current is IB, and here the current is IC, and current flowing in this is IBC. IBC from B to C, the current is IBC. First of all, we should need a balanced load. Generally, in three-phase system, the three phases are displaced with 120 degrees each other. But in two-phase, the two phases are displaced by 90 degrees only. Displaced by 90 degrees only, VA and VB. Next, for balanced load, nothing but VA is exactly equals to VB. For balanced load, VA is equals to VB. Let's see here. For example, this is VA and this is VAD. N2 by N1 or E2 by E1. E2 by E1 is equals to N2 by N1, right? What is E2 by E1 here? E2 is the VA. E2 by E1. E1 is equals to VAD. E2 by E1 is equals to N2 by N1. N1 is taken as N2 by N1. This is, and next here also E2 by E1. What is that? E2 is the VB, and what is E1? E2 is the VB. What is E1? E1 is the VBC. E1 is the VBC. E2 by E1 is equals to N2 by N1 is equals to N2 by N1. E2 by E1 is equals to N2 by N1. From this VA is equals to VAD into N2 by N, and from this VB is equals to VBC into N2 by N1. Here I said you balanced load, VA is equals to VB, equal them. VAD is equals to, VAD into N2 by N is equals to VBC into N2 by N1. N2 gets cancelled out. N2 gets cancelled out. N2 gets cancelled out. Then N is equals to, I want N. N is equals to VAD by VBC of N1. VAD by VBC of N1. N is equals to VAD by VBC of N1. Nothing but, let's see here, we have a three phases in delta. For example, this is taken as delta. A, B, C, VAB, VBC, VCA. And here on BC we have a point D. This is voltage V. This is totally voltage V. So this is V by 2 and this is V by 2. This is totally the phase voltage V. So CD V by 2 and DB V by 2 and ABV and CAV, everything. This is three phase. Of course, we have, if you want a star connection, take this is a neutral point like this. This is a star connection. Right. What we want here, N is equals to VAD by VBC of N1. VAD by VBC of N1. Can you tell me what is VBC? VBC is equals to V by 2 plus V by 2. VBC is equals to V. Can you tell me what is VAD? What is VAD? According to Pythagoras, calculate VAD. According to Pythagoras, calculate VAD. So calculate VAD. This VAD is equals to square root of V square minus V by 2 whole square. So what is the answer? If you calculate this, what is the answer? V square and V square by 4, nothing but root 3 V by 2. Yes or no? Root 3 V by 2. Yes or no? If you calculate this, 3V square by 4, then root 3V by 2. Nothing but VAD value is root 3 by 2 times of V into N1. V gets cancelled. So N is equals to root 3 by 2 times of N1. N is equals to, for balanced load, the N value is not fully considered. The n value is not fully considered. The n value is root 3 by 2 times of root 3 by 2 times of n1. This is root 3 by 2, nothing but 86.6%. 86.6%. Now this is our A, and here the current is IA for balanced load. For balanced load. So how much this is? This is root 3 by 2 times of n. Root 3 by 2 times of n1. What is n? N value is root 3 by 2 times of n1. Nothing but the teaser transformer's primary for balanced load. The teaser transformer's primary tapped up to 86.6% only. To get the balanced load, the teaser transformer's primary tapped up to 86.6% only. And this teaser transformer's primary cuts the main transformer's primary in 50:50 ratio. Nothing but exactly perpendicular. Exactly perpendicular. So the angle between primary of the teaser and main primary is 90 degrees. Remember this. The phase shift between these two primaries is 90 degrees because it cuts the main transformers exactly 50-50. That's why the phase shift between these two is exactly 90 degrees. Remember this. Exactly 90 degrees. Remember this. And the phase shift between two secondaries. What is this secondary? Secondary is a two-phase system. Secondary is a two-phase system. So two-phase system, the phase shift between two phases is 90 degrees. Here two primaries are displaced by 90 degrees and two secondaries are also displaced by 90 degrees. This is for the Scott connection. This is for the Scott connection diagram. This is the Scott connection, nothing but the conversion of three-phase to two-phase or two-phase to three-phase, any, no problem. But for easy analysis, here we have a three phases A, B, C, but here we have only two phases VA and VB, IA and IB. But here I have a three currents IA, IB, IC. But here I have only two currents IA and IB. This is why we are taking only 86.6% for balanced load. For balanced load, the number of turns on the teaser transformer is root 3 by 2 times of N1. Therefore, turns ratio of teaser transformer, turns ratio of teaser transformer is, turns ratio of teaser transformer is 0.866 or root 3 by 2. 0.866 or root 3 by 2. This is the turns ratio of teaser transformer. Okay, what I said you, once listen carefully. Scott connection, nothing but the conversion of three-phase to two-phase or two-phase to three-phase. Here we have two identical transformers. One transformer is called teaser transformer, one transformer is called main transformer. The teaser transformer cuts the main transformer in 50:50 ratio. That's why the two primaries are displaced by 90 degrees. And here two secondaries are connected to a two-phase load. Nothing but these two secondaries are also displaced by 90 degrees. These are also displaced by 90 degrees. And to get the balanced load, the number of turns on the teaser transformer's primary, is equals to root 3 by 2 times of N1. Nothing but this is tapped up to 86.6% only. This is tapped up to 86.6% only. Hence, the turns ratio of teaser transformer is 86.6%, nothing but 0.866 or root 3 by 2 or root 3 by 2. This is up to the Scott connection diagram, just up to diagram. Are you okay? Up to diagram. Now, Now I want this star neutral. I want this neutral where I have to take the neutral point in this diagram. Where I have to take the neutral point in this diagram. Tell me in this diagram where I have to take the neutral point. Generally, the neutral should be taken to get the balanced input supply. To get the balanced input supply, the neutral should be taken to get the balanced input supply. For that, the neutral is placed on the teaser transformer. The neutral is placed on the teaser transformer with 2 is to 1 ratio, with 2 is to 1 ratio, or 2 is to 1 ratio, or 57.7% is to 57.7% is to 28.9%, 28.9%. 28.9% and 57.7%. Neutral point placed on teaser transformers primary, teaser transformers primary at 2 is to 1 ratio, or 57.7 is to how much percentage less than 86.6%? 57.7 plus, to get the 86.6, here we have to take around 29 percentage. 29, but not exactly 29, around 28.9 percentage. 57.7 is to 28.9. The neutral placed on the teaser transformer at 2 is to 1 ratio to get the balanced load. Sir, to get the balanced supply. Sir, how it is balanced, sir? Sir, how it is balanced, sir? Tell me. What I am telling you, the AN is exactly equals to BN is exactly equals to CN. What I told you, the AN is equals to BN, that is equals to CN. Is it correct or not? Tell me first. Balanced supply, right? Balanced supply, nothing but the three phases should be same. The three phases should be same. So tell me, is it correct or not? Yeah, how it is correct, sir? AN, of course, 57.7%. AN is the 57.7%. AN is the 57.7%. But what about BN? BN is nothing but BD plus DN. BN is nothing but BD plus DN. CN is nothing but CD plus DN. CN is nothing but CD plus DN. Of course, this is 57.7% okay, but BN, let's take it. This is 50% and this is 28.9%. Again, this is here also. This is CD is 50% and DN is 28.9%. Now calculate it how much it is. This value also 57.7%. This value also 57.7%, and option A also, AN also 57.7%. All are balanced. The balanced supply is given to the system. 50 square plus 28.9 square is equals to 57.7, and 50 square plus 28.9 square both are same. So AN is equals to BN is equals to CN is equals to 57.7 percentage. 57.7 percentage. This is what the Scott connection. To get the balanced load, the teaser transformer capped up to 86.6%, and to get the balanced supply, neutral placed on the transformer in 1:2 ratio, or 28.9:57.7 ratio. This is about the Scott connection. This is about the Scott connection. Then here we have a small derivation and vector diagram. Let's see that vector diagram. Okay. Right, see sir. This is our Scott connection diagram. And here the primary is 3-phase, secondary is 2-phase. Nothing but, let's see here. This is a point A and this is B and C. And the load is 2-phase. Load is 2-phase. This is VA and VB. VA and VB. This is like this. Here, for example, the load IA is lagging VA by an angle phi. This is lagged by angle phi. And balanced load, that's why IB also lagging by phi. This is balanced load, that's why IA is equals to IB exactly. For example, if the load is operating at 30 degrees lagging, then our TZ transformer also operating at 30 degrees lagging. If the load is operating at 10 degrees lagging, then our TZ transformer also operates at 10 degrees lagging. Nothing but the load and the TZ transformer operates similarly. That's why here, if IA is lagging VA by phi angle, then our IA also lagging this VA by angle phi. And next one, here IA and IBC. IA and IBC exactly 90 degrees to each other. That's why the IBC current should be like this. The IBC current, this is IBC. If this is IBC, this is minus IBC. If this is IBC, this is minus IBC. This is IA and IBC 90 degrees to each other. Yes or no? If this is IBC, this is minus IBC. Next one, IB to C, IBC. In this way, C to A minus IBC. This is one. Now I want IB as well as I want IC. IB and IC. To get IB is equals to this IBC minus IA by 2. IB is equals to IBC minus IA by 2 minus IA by 2. And IC is equals to in opposite direction. IC is equals to minus IBC and this IA by 2 also in opposite direction. IA by 2 also in opposite direction, minus IA by 2, minus IA by 2. We have to calculate these two words. So how we can calculate? Actually, when this angle is phi, this angle is also phi, and this angle is also phi, lagging by phi an angle. Now I want IBC. Tell me how I can calculate IBC. I want to calculate IB. IB is equals to IBC minus IA by 2. How we can calculate minus IA by 2? This is IA. So I have to take negative direction for minus, but magnitude also only 50%. This is minus IA by 2. And here also, this is minus IA by 2, and sum of these two is our IB. Sum of these two is our IB. IB is equals to IBC and minus IA by 2. IBC minus IA by 2 is equals to IB. In generally, this angle is 30 degrees. As usually, IC is equals to minus IBC minus IA by 2. Then this is our IC. This is our IC. This is our IC. And of course, this angle also 30 degrees. This angle also 30 degrees. This is the vector diagram at balanced load. Vector diagram at balanced load. If load operating at 5 degrees lagging, if load operating at 5 degrees lagging, then teaser transformer operates at 5 degrees lagging. Teaser transformer operates at 5 degrees lagging. Then main transformer operates at main transformer nothing but we have a two parts. Main transformer nothing but we have a two parts. Main transformer operating at one is, see here, one is 30 plus 5 degrees, 30 plus 5 degrees, and other one is, see here, other one is, now calculate this one. How much is this? How much is this? This is 5 minus 30 degrees. Yes or no? 5 minus 30 degrees. So one transformer is operating at 5 plus 30 degrees. Other transformer operates at 5 minus 30 degrees. If load is operating at 5 degrees lagging, then our teaser transformer also operating at 5 degrees lagging, but remaining two parts of the main transformer, one is operating at 5 plus 30 degrees, and other one is operating at 5 minus 30 degrees. One is operating at 5 plus 30 degrees and other one is operating at 5 minus 30 degrees. This is at balanced load condition. Sir, I want IB and I want IC. You forgot about this. I will give you IB and IC. For that, calculate from this. N2 by N1 is equals to I1 by I2. N2 by N1 is equals to I1 by I2. We know that. So what is N2 here? N2 is only N2. N2 by, what is N1 here? Root 3 by 2 times of N1. N2 by N1. N2 by N1 is equals to I1 by I2. What is I1 here? IA. I1 by I2. What is I2 here? IA. From this, IA is equals to, tell me sir, from this IA is equals to, IA is equals to capital IA into N1 by N2 into 2 by root 3. Yes or no? IA is equals to, 2 by root 3 or root 3 by 2? Root 3 by 2. This is completely goes here. When IA comes here, IA N1 by N2 into root 3 by 2. This is my IA from this diagram. And from this diagram, again calculate from this diagram. Tell me sir, what is answer? N2 by N1 is equals to, again N2 by N1 is equals to I1 by I2. What is I1 here? I1 is the IBC. So I1 by I2. I2 nothing but IB. Now tell me, what is IB from this? IB is equals to IBC into N1 by N2. So from this, I want capital IA. From this, I want capital IA. Capital IA is equals to N2 by N1 into capital IA is equals to N2 by N1 into 2 by root 3 into IA. This is capital IA. Remember this. This is very important. I will ask you again. IA, important. I will ask you later. Remember this. And from this IBC is equals to N2 by N1 into IB. This is IBC. Now we have to calculate. This IB. IB is equals to IBC minus IA by 2. These two vector sum, and the angle between these two is 90 degrees. The angle between these two is 90 degrees. The angle between these two is 90 degrees. Hence, IB is equals to square root of. What is IBC? What is IBC here? IBC is equal to N2 by N1 into IB. So, N2 by N1 into IB whole square plus, even though minus, but in vector sum it is plus, IA by 2. What is IA? This is IA, but we want IA by 2 whole square. IA by 2 nothing but N2 by N1 and 2 by root 3 and IA and 1 by 2, because IA by 2 whole square, 2 gets cancelled. And I said you IA is equal to IB. So substitute in terms of IA and IB. Now tell me what is the answer. The answer is square root of N2 by N1 whole square IA square. N2 by N1 whole square IA square common. N2 by N1 into IA whole square common. This is common. So this is 1 plus, tell me sir, 1 plus, how much is there? 1 by root 3. 1 plus 1 by root 3 square. 1 by root 3 square nothing but 1 by 3. Now tell me sir, what is the answer? 1 plus 1 by 3 nothing but 4 by 3. What is this value? This value 4 by 3. So N2 by N1 IA 2 by root 3. 4 by 3 nothing but 2 by root 3. This is equals to IB. IB is equals to N2 by N1 into IA into 2 by root 3. I said you remember IA. This is very important. I said you see these two equations. IA is equal to N2 by N1 into 2 by root 3 into IA. IB is equals to N2 by N1 into IA into 2 by root 3. Same. If you want to calculate IC, even IC also, this is only the derivation. For IC also, this is the derivation, because IBC square and IA by 2 square. IBC nothing but N2 by N1 into IB, but IB is equal to IA whole square plus, because of vector sum, plus IA by 2 whole square. Again, this is equals to IC. IA is equals to IB is equals to IC. All are equal. That is N2 by N1 into 2 by root 3. This is the Scott connection, which gives us a balanced load and balanced supply. Balanced load, IA is equal to IB, and the supply, IA, IB, IC, both are, all the IA, IB, IC, all are same. This is what the Scott connection vector diagram with balanced load and same lagging loads. Now, let's draw the vector diagram for unity power factor. Only one vector diagram. For unity power factor, let's see. For unity power factor, you should remember these things. You should remember IA. If you remember IA, you can remember IB and IC, because all are same. So, let's draw the vector diagram for unity power factor. Load operating at unity power factor. Let's draw here. For example, this is VA and this is VB. I said you that load is operating at unity power factor, nothing but IA in phase with VA and IB in phase with VB, IB in phase with VB, and here take the supply vectors like this. This is A and this is B and this is C. I said you, if load is operating at unity power factor, then teaser transformer also operating at unity power factor. Teaser transformer also operating at unity power factor. And this IA and IBC is operating at IA and IBC operating at 90 degrees to each other. 90 degrees to each other. This is, for example, IBC and this is minus IBC. IBC and minus IBC. IBC and minus IBC. Now let's see. This is my IA and this is my IBC and minus IBC. I want IB. To get IB is equal to, I said you already, IB is equals to IBC minus IA by 2. And IC, to get IC also, minus IBC minus IA by 2. And if you combine them, then this is called IC and this is called IB. This is the angle of 30 degrees. I said you already, this is the angle of 30 degrees. So what you conclude from this? If the load is unity power factor, if the load operating at unity power factor, then teaser transformer also operating at unity power factor, and the main transformer operates at unity. That's why one is operating at 30 degrees lagging and other one is operating at 30 degrees leading. See here, this is 30 degrees lagging, but this is 30 degrees leading. This is 30 degrees lagging. I said you already, one is operating at 5 plus 30, other one is operating at 5 minus 30. Here 5 is the 0. This is the vector diagram for balanced lagging load. This is the vector diagram for balanced unity power factor load. This is about Scott connection. Sir, where we are using Scott connection? Generally, the Scott connection nothing but conversion of 3-phase to 2-phase. In generally, the supply source is most of the cases 3-phase only. But in some industrial applications, like a welding furnaces, arc welding like that, in welding furnaces and in some special cases, we require 2-phase supply. In that conditions, by using Scott connection, we can convert 3-phase system into 2-phase system. We can convert 3-phase system into 2-phase system. This is the applications of Scott connection. In furnaces also, by using 2 single-phase furnaces, we can convert into 3-phase. Or by using 3-phase system, we can use 2 single-phase furnaces. In that condition, where we require 3-phase to 2-phase conversion, at that condition, we can use this Scott connection. This is about Scott connection, very important for us. Thank you.